Hi, my name is Dmitry and I am presenting the paper entitled Lower Bounds for Regular Resolution of Parities, which was written in collaboration with Klimi Fremenko and Michal Ganty. The paper is devoted to propositional proof complexity. The main notion in this area is the notion of a proof system. The propositional proof system is a formal way to certify that a given formula in the conjunctive normal form is unsatisfiable. It is known that class NP does not equal class co-NP if and only if, for any propositional proof system, there is a family of hard formulas that do not have polynomial size proofs. The famous research program in proof complexity was introduced by Stephen Cook is to prove superpolynomial lower bounds on the proof size in particular proof systems. Ideally, proving lower bounds for stronger and stronger proof system, we come closer to proving NP does not equal NP. In this talk, we consider only refutational proof systems that derive contradictions from the axioms that are clauses of the refuted formula. The intermediate statements in such refutation are called proof lines. In Frege proof systems, proof lines can be arbitrary Boolean formulas. Each particular Frege proof system uses some sound and implicationally complete set of rules. All Frege systems are equivalent and equivalent to standard Hilbert's propositional proof system from logical textbooks. For Frege, unfortunately, we don't know any superpolynomial lower bound. However, if we bound the depths of formulas that are used as proof lines, then we can prove lower bounds. Bounded depth Frege operates constant depth formulas over the basis of conjunction, disjunction, and negation. 30 years ago, I proved the superpolynomial lower bounds for this proof system using a switching lemma. And here we have a similarity with the field of formula and circuit complexity, where the main problem is proving lower bounds on the size of formulas of circuits computing explicit Boolean function. In bounded depth case, lower bounds are known, and in unbounded case are not known. The used basis is important for bounded depth formulas since, for example, parity requires exponential size constant depth formulas. If we consider a system where in formulas we can use parities, we get proof system bounded as Frege with parity gates. And we don't know any lower bound for this proof system. And here we have a difference between proof and circuit complexity since there are known lower bounds in the case of basis with parities for size of circuits or formulas due to Razborov and Smolensky. However, the result of Razborov and Smolensky gives us hope that it is possible to prove lower bound in the proof complexity settings as well. The weakest subsystem of bounded depth Frege, for which we still don't know how to prove superpolynomial lower bounds, is resolution over parities. This proof system extends the plane resolution. Plane resolution is the most studied proof system where proof lines are clauses or disjunction variables or their negations. Resolution of the parities operates with disjunction of F2 linear equations. It turns out that proving lower bounds for resolution of a parity is a very challenging question. Many researchers try to prove the lower bound, but succeed only in tree-like case. The first superpolynomial lower bound for tree version was proved 10 years ago by Dmitry Sokolov and myself. Since that time, many approaches for proving lower bounds in tree case were developed. In this paper, we make significant progress and prove first lower bound for an essentially DAG-like fragment of resolution of the parity, regular resolution of a parity. Regular resolution of parity is defined similar to the regular resolution. This proof system is strictly stronger than both tree-like resolution of the parity and regular resolution. The main result of our paper is an exponential lower bound for this proof system. We start with the definition of resolution. Proof lines are clauses, and the system has two rules. The resolution rule can be applied to two clauses that have variable x with different signs, and we can resolve this variable. And the weakening rule allows adding new literals in a clause. In a resolution of a parities, proof lines are linear clauses that are the disjunction of linear equations over the field of two elements, or equivalently, the negation of F2 linear systems. In the resolution rule, we can resolve the value of F2 linear form. The weakening rule here is much more stronger than we have in plain resolution. We can derive a linear clause from a linear clause, any linear clause that is semantically followed by the former clause. A refutation of a formula phi is a sequence of clauses, plain or linear, such that the last clause is empty, the contradiction, and every clause is either an axiom of the initial formula or is obtained from the previous by the rule. In 1987, Ulkers showed that there are unsatisfiable F2 linear systems that require exponential resolution proofs. And it's rather easy to see that all unsatisfiable F2 linear systems are easy for resolution of a parity, and it is true even in tree-like case. There are many papers establishing lower bounds for tree-like resolution of a parities that are quite many different approaches, including proof-layer games, reductions from randomized communication complexity, reductions from polynomial calculus degree, and I also want to mention recent papers introduced lower bound where lifting from resolution depths. Let us define regular resolution. In a regular regime, with every clause, we also say the set. With every clause C, we can also say set VC, variables that were resolved in the derivation of C. It is allowed to resolve clauses C and D over variable X if X doesn't belong to the union of VC and VD. In regular resolution of a parities, we similarly define for every clause C the set of linear forms LC that were resolved in the derivation of C. Now it is allowed to apply the resolution rule to linear clauses C and D over a linear form F only if F does not belong to the span of LC and to the span of LD. It is easy to see that regular resolution of a parity simulates regular resolution. Greznov, Pudlak, and Talibard-Farts show that regular resolution of a parity simulates tree-like resolution of a parities, and it is also known that regular resolution can be stronger than tree-like resolution of a parities. Thus, we can conclude that regular resolution of a parities is strictly stronger than both regular resolution and tree-like resolution of a parities. We will only use the following simple property of regular resolution. Assume that there is a path from the empty clause to a linear clause C of length t, where we count only application of resolution rules. Then the dimension of LC is at most the maximal dimension that equals the number of variables of formula phi minus t. Oh, this property is very straightforward. And now we are ready to formulate our main result. The hard formula that we use is the binary pigeonhole principle. It states that there are m distinct binary L-bit strings. The statement is false if m is greater than 2 to the L. In other words, we will say that we have m pigeons and we have to put them to 2 to the L different holes. xi is the bit address of the hole where the ith pigeon flies. The variables of binary pigeonhole principles are two index variables x, I, j. They correspond to the bits of the string xi. Clause states that for every pair of pigeons a and j and every hole a, either the ith pigeon is not in the hole A or the jth pigeon is not in the hole A. It is easy to see that this statement can be represented as a clause. Our main theorem states that any regular resolution of a parity refutation of the binary pigeonhole principle, where the number of pigeons equals the number of holes plus 1, has at least exponential size. Let us start with a high-level overview of the proof strategy. We consider a random walk in the regular resolution refutation of the binary pigeonhole principle. We choose a random full assignment sigma and start the path in the empty clause and make t steps. Each time we go from the clause to a premise of this clause that is falsified by sigma. When we say t steps, we continue on the application of resolution rule. Let C be a clause where we stop. The first step is to prove that the negation of C, recall that it is a linear system, has a large rank with probability at least 1/2. Okay, and then we note that the random assignment satisfies the linear system with rank R with probability exactly 2 to the minus R. We also know that sigma satisfies the negation of C. Hence, C can be the end of the part with exponentially small probability, each particular C. Hence, there should be exponentially many such clauses C. In the proof of a lower bound, we consider the set of axioms. Clauses of the binary pigeonhole principle that are used to derive the linear clause C. And we separately prove lower rank lower bound in two different cases. In the first case, the set of axioms A mentions a small number of pigeons. And in the second case, A mentions a large number of the pigeons. We start from the first case, where the set of axioms mention small number of pigeons. Let us discuss the main ideas of the first case, where the set of axioms from which clause C is derived mentions a small number of pigeons. In this case, we demonstrate our main technical tools. Consider a matrix in variables of the binary pigeonhole principle. On the picture, we enumerate columns such that first of all we enumerate variables corresponding to the first pigeon, then the second, and so on. We say that the matrix is safe if there is a basis of the set of columns of this matrix such that for each pigeon, the basis contains at most one column. On the picture, the basis columns are green. The key idea is that if we have a satisfiable linear system with a safe matrix, then we can construct its solution as follows. Take arbitrary values for all non-basis variables, and then all values of all basis variables are uniquely determined. So we do not control at most one bit for every pigeon. Okay, consider the following lemma. Let C be a semantic implication of a set of axioms A, and assume that A mentions all but R pigeons. Assume also that the matrix of the negation of C is safe. We claim that the rank of the negation of C is at least R. For the sake of contradiction, assume that the rank of negation of C is less than R. Our goal is to construct a solution of negation of C such that it sends all pigeons mentioned in A to different holes. We will get a contradiction since this solution should satisfy all axioms of I, but it falsifies C. A contradiction with semantic implication. So we have n plus 1 minus R pigeons and n holes. By our assumption, we have at most R minus 1 elements in the basis. For pigeons that have elements from the basis, we reserve 2 holes that differ only in the value of the coordinate from the basis. For other pigeons we reserve distinct holes. By the property of the safe matrix, we get that we can construct a solution where we use only reserved holes. But in this lemma, we indeed get a good rank lower bound, but we assume that the matrix is safe. Unfortunately, this is not necessarily the case. Okay. Here we start from the last lemma. The disadvantage is that we recur that the clause C is safe. Now assume the weaker requirement. Namely, we assume that there is a partial assignment that assigns a small number of pigeons to the different holes, such that the application of this assignment to the negation of C is satisfiable and has a safe matrix. It is easy to see that the argument works well in this case too, because this assignment row injectively saves some set of pigeons. Okay. Consider a matrix in n variables of the binary pigeonhole. We say that the closure of this matrix is the inclusion minimal set of pigeons S, such that if we remove all columns corresponding to this set S from the matrix, we will get a safe matrix. For example, in the picture, we denote the set of deleted pigeons by black. It can be shown that the closure is unique, and we denote that it is a closure of M. It also can be shown that the size of the closure is at most the rank of the system, or the rank of the matrix. The notion of the closure is our main technical tool. Informally speaking, pigeons from the closure of a linear system are the pigeons that linear system speaks about. In a solution, we should carefully choose holes for the pigeon from the closure, and after that we get a safe matrix where we can choose holes almost arbitrarily. Only one bit is not under our control. A linear system with few equations can mention almost all pigeons, but its closure is always at most the number of rows. So the first lemma on the slide works well if node C has a small rank and it has a solution that is injected on the closure on the matrix. Now let's go back to the random walk. Recall that we consider regular resolution of the parities reputation of the binary pigeonhole principle. We take a random full assignment sigma and make t steps on the path from the empty clause, each time going to a premise falsifying by sigma. And we calculate only steps corresponding to resolution. And let C be the last linear clause. And let M be a matrix of negation of C. It is rather straightforward that the rank of matrix M is at most C, is at most T. We claim that sigma is injective on the closure of M with probability at least 1/2. Notice also that sigma satisfies node C. So this lemma is precisely what we need to finish the proof. Assume for simplicity that M does not depend on sigma. Then the statement of the lemma is true just because of the paradox. The size of closure is at most T, and T is a small. Then the random assignment is injective. Unfortunately, M does depend on sigma, and a more complicated argument should be used to prove this lemma. And now consider the second case where the set of axiom A mentions many pigeons, or in other words, contain many variables. In this case, the regularity plays a role. Consider regular refutation of a parity, regular resolution of a parity reputation of a formula phi. Consider a clause C for which there is a path from the empty clause to it of length t. We count only resolution rules. Let C be essentially derived from the set of axioms A. We include a clause of phi in A, only such axioms such that there is an assignment falsifying C such that if we start a path from C going to F falsified by sigma premise, we achieve this clause of phi. The lemma states that the rank of the negation of C is at least T minus the number of variables that are in phi but not in A. Lemma is proved as follows. First of all, recall that in regular proofs, the dimension of LC is at most number of variables in phi, maximal dimension, minus T. We claim that the dimension of LC plus the rank of negation of C is at least the number of variables of A. Indeed, for every axiom of A, there is an assignment and the path from C to this axiom such that the assignment falsifies all clauses on this path. Consider the following example of application of resolution rule. Let an assignment falsify C or D. Then if in this assignment F equals 0, then it falsifies the right premise. And if F equals 1, then falsifies the left premise. So we can assume that the edges of the refutation graph are labeled with linear equations. And the system of equations consisting the equations from negation of C and from the red path is satisfiable, and every solution of this system falsifies our axiom. Hence, every particular variable of this axiom is fixed by the linear system. Hence, this variable belongs to the span of linear forms from C and from the path. And LC consists of all linear forms from all paths from C to axioms. Hence, this inequality holds. Now, from these two inequalities, we conclude the lemma. The bound given by lemma is good if A contains almost all variables, and this is precisely our case. Okay. Very recently, it was proved that resolution of a parities is strictly stronger than regular resolution. The proof uses our technique combined with some lifting. The interesting open questions are to consider other definition of regularity. For example, we can define regularity by saying that the resolving linear form does not belong to the span of linear form that are used in the resolution rule in descendants of the current clause. Another interesting definition of regularity, weaker than the two previous, is to require just that all linear forms in all paths are linearly independent. And of course, the main open question is to prove a lower bound in the unrestricted case. Thank you for your attention.